Hi guys, welcome back to Chem Talks. Today in Chem Talks we're going to talk about the periodic table. A little bit about its history, how it was created, and how the original periodic tables differ from the one we use today. Then we're going to talk about the groups in the periodic table, how elements are arranged, and they're based on different groups and classes based on their characteristic. Remember, the periodic table is essential to chemistry. As I've said all along, it's basically your ultimate cheat sheet for chemistry. So the better you understand it, the better you'll be able to use it and better you'll be able to do in class. So let's go ahead and get started. The first periodic table was published in about 1869 by Dmitri Mendeleev. There was also another German scientist working at about the same time who published as well, and they both came up with the same idea about the periodic table, but Mendeleev is who's usually credited with having discovered it. What Mendeleev did, he was looking at the 60 or so known elements at the time, and he basically had this information put on note cards, and he was looking at them, and when we looked at the characteristics of them, he noticed that there was a reoccurrence in both the physical and chemical properties of certain elements. So he started laying his cards out by placing elements with the similar properties next to one another and created this periodic table. The really interesting thing that he did was he left some blanks in this table, and these were for missing or undiscovered elements. And what we found is that within about 50 years of Mendeleev publishing his periodic table, all those blanks began to be filled in. So his leaving those blanks was a brilliant idea. Mendeleev arranged his periodic table by their atomic mass. Remember, atomic mass is the weighted average of all the sub-7 elements. They are arranged from lowest atomic mass to increasing atomic mass. This is what Dimitri's original periodic table looked like. If we put it in a form that we're more familiar with today, it looks something like this. And you'll see these yellow blocks are the missing elements, or the places that he said, hey, there should be something here, but we haven't discovered yet, so I'm just going to leave it blank. Pretty impressive. Our modern periodic table is based on a work of Henry Moseley. Moseley was an English physicist, and what he did, he used X-rays to determine the atomic number of elements. That is, to determine how many protons were in the nucleus. So Moseley determined the nuclear charge, that is, how many protons were found in the nucleus. And he built on Mendeleev's theory of this repeating units, okay, this repeating trends. But unlike Mendeleev, he arranged his by increasing atomic number. This is something Mendeleev didn't know about. So as we got better science and more advancements in technology, we were able to come up with the atomic number. An interesting fact about Moseley was that he was killed in World War I at the age of 28. So he still had his whole life ahead of him. Imagine what other discoveries he could have made in the area of physics and chemistry if he wouldn't have been killed. And as a result of his death, the British government no longer assigns scientists to combat duty in times of war. They keep them in the back where they're safe. They don't want to lose another genius like Moseley. Okay, the modern periodic tables are arranged into rows and columns according to having similar properties and their increasing atomic numbers. Okay, what Moseley did was he was able to more accurately explain the periodic law that Mendeleev came up with. And the periodic law says that when elements are arranged by their increasing atomic number, there is a repeating pattern, or what we call a periodic pattern, in their chemical and physical properties. And this is what sets up the look of our modern periodic table, these repeating properties. So the periodic table is organized into periods, which are horizontal rows. So going this way, they're numbered 1 through 7. Okay, they're also sometimes called series. We will refer to them more as periods in class. Now going the other way, we have groups. These are vertical columns, and they're also called families. So groups or families are used interchangeably. Okay, and they're named, these groups are named by a number and a letters. So example, we have 1A, 2A, 3A, 4A, all the way up to 7A, or we'll have the B's, okay, 1B, 2B, 3B, and so on. And depending on what your periodic table looks like, you may or may not see this organization. Some of them just label them 1, 2, 3, 4, 5, 6, 7. It varies depending on what periodic table you're using. Okay, the group 1A through 8A, these are what we call our representative elements. Okay, our group 1B through 3B, these are known as our transition elements. And then our two rows down at the bottom, these are called the rare earth metals, are also known as intertransition elements, because if we look, they should be put up kind of in the middle or at the beginning of the transition elements. But we don't put them there because it would make our periodic table look weird. So they do have something called a long periodic table, which puts in there, but we're not going to use that version. So let's take a look at these representative elements. So here we can see in our periodic table, the white is a representative. Here's our transition in the middle, and then our rare earth metals down at the bottom. Okay, natural elements. These are elements 1 through 92 as far as atomic number goes. They're found in nature either free form, like gold, may just find a gold nugget, or in a combined form, such as sodium. Sodium is really reactive. And if it was out there by itself, it's going to easily react with water. So generally we find it combined with some other element. Okay, the natural elements, if we look at as far as their abundance in the universe, the most abundant is hydrogen, makes up about just over 3/4 of the universe, followed up by helium. So two elements, atomic number 1 and atomic number 2, make up the majority of our universe. If we look at the Earth's crust, the most abundant is oxygen, about 49.5%, followed by silicon, and then aluminum, iron, and then calcium. Don't worry, I won't ask you the percentage of these. Well, those are the most abundant. What's the rarest? Well, the rarest natural element is astatine, AT. Not a lot is known about it because at any one time there's probably less than 28 grams of it here on Earth. It's highly unstable. Okay, so not a lot is known about it. We'll see some of the issues that brings up later. Okay, the transuranium. These are elements 93 and beyond. Okay, many of these are prepared from other elements. In other words, scientists combine different elements to make these. Okay, they're radioactive, meaning they break down. We talked about that with isotopes being stable and unstable. See, many of these are unstable. Beyond atomic number 103, these may exist for only a split moment in time. So scientists create them really quick and then they break apart. So it's really hard to get a lot of good information on them. Interesting one is numbered 98, californium. This is the most expensive element out there. It's a man-made one, and it's about $1,000 per microgram. What's that mean? Well, let's put in something that makes a little more sense. That runs $350 billion per pound. Okay, makes gold look really cheap. So you want to be rich, find a way to get a pound of californium. Okay, we can also look at the elements in terms of classes. And there are two general classes of elements on the periodic table. There's metals and nonmetals. And there's a third group which kind of falls under nonmetals called metalloids we'll talk about. So let's look at the characteristics of these. Metals. Think about a metal you know. Think about aluminum. Okay, maybe wire, copper wire. Okay, iron from your car. Think about those when you think about characteristics of metal. Generally, they're going to conduct electricity and heat really well, right? We use copper wires in our house to conduct electricity. If you have speaker wires, you want really good speaker wires, they're going to be gold-plated because they help conduct electricity. Okay, they're malleable, which means they can be rolled into thin sheets. Think about aluminum foil used for cooking. Think of how thin that is. They're luster, meaning they're shiny. They reflect light well. Look at the can, how well it can shine it. Okay. But what we see is that some, even though it's a luster is a characteristic, some must be polished due to oxidation. Think about the Statue of Liberty, right? Made of copper, but it's kind of got that greenish oxidation. So if we shined it up really good, we get a nice shiny Statue of Liberty. Okay, they're ductile, meaning the metals can be drawn out on a thin wire. Think about copper wire. They're tenacious, which means they can resist stretching. They don't stretch at all. Okay, let's look at some of the groups. The first group, 1A, the first column, these are the alkali metals. Okay, they are highly reactive. Okay, they're not, because they're so reactive, they're not found in nature uncombined. They're generally hooked up with some other element. Okay, they have violent reactions with water. We're going to see this in a demo we do in class. Generally, when you throw some of these in water, what they're going to do is produce hydrogen gas and a metal hydroxide, which is a base. Think about what you know about the Hindenburg. Remember the Hindenburg blimp? It was filled with hydrogen and exploded? Okay, well, you put these things in water and you're going to get some good explosion going on. Okay, generally they're soft. Some of them are so soft you can actually just cut them with a knife. We'll cut sodium with a plastic knife in class even. And they generally have a low melting point, which means they melt at a low temperature. Okay, and they're good conductors, as we kind of already talked about. And they're the first column right here is our alkali metals. Next to them, the next column is what we call the alkaline. Don't get that confused with alkali earth metals. Very similar characteristics to alkali. They're reactive, not found uncombined. They react with water to produce a hydrogen gas once again in the metal hydroxide, which is a base. Okay, they extract it from mineral ores because they're so reactive. They generally will tarnish pretty fast, which means they get a gray look. They almost have a gray luster to them. And they are found in our second column here. Let's jump to the other side of the periodic table, to our nonmetals. Okay, nonmetals basically have the opposite characteristics of metals. They're poor conductors of heat and electricity. They're brittle as salt, meaning they break easily. They're not ductile, meaning they can't be drawn in wires. They're not malleable, they can't be pounded flat. We'll talk about two groups of nonmetals. Group 7A is the halogens. Okay, these are all nonmetals. And if we look at the bottom of the halogens, we have acetine. Now, acetine I put question mark because we're not sure if it's a nonmetal or metalloid. The actual thinking right now is it probably falls more into metalloid. Remember, there's such a small quantity of it here on Earth that we don't know a whole lot about it. Next to the halogens are our group 8A, or the noble gases. Okay, this is from helium to radon. These guys are inert, meaning no chemical activities, meaning they don't react with other chemicals. Scientists have got them to react in the lab, okay, with each other, but other than the forcing them, they're pretty unreactive. Okay, they're what we consider to be a completely stable atom. So if we look at our periodic table here, here is the halogens, and here are our noble gases, okay, on the far right-hand side. Now the third group I talked about was your metalloids. Metalloids are non-metal elements that have metal-like properties. So they kind of metalloids, metal-like. They have nonmetals with metal properties. Okay, this forms a zigzag line on the periodic table. And if we look at the elements, they're going to be found on either side of that. And I put it once again, here they are, and I put a question next to acetine because we're not positive. They think it's a metalloid based on what they've been able to discover so far. So we're going to consider it to be a metalloid for our purposes of chemistry. And there is our metalloids, that zigzag group. So to the left of them over here, you have your metals. To the right of them, you have your nonmetals. Down here, right, these are going to be, should be up here, so they are going to be metals as well. One last thing I want to talk about, and that's some periodic trends in it. We're going to look at what we call the atomic radius. Remember, radius gives us an idea how big an atom is. And we're going to see two different trends based on whether we're talking periods or groups. When we talk about periods that's going across, the radius is going to shrink as you go across. The reason is as you go across a period, you're not adding any more orbital shells. You're not getting any wider, but what you are adding is protons. And protons are positive. They're attracted to negative electrons, and so they tend to hold the electrons tighter and scrunch them in. Okay. Now, as we go down a group, it's going to increase. The reason is each time we go down a group, we're adding a new orbital. Okay, so it gets bigger and bigger and bigger. Okay, so guys, what I want you to be able to get out of this is to understand how the periodic table is arranged, and also be able to put elements into different groups based on their characteristics. And, you know, are they a metal? Are they a non-metal? Are they metalloid? Are they alkali, alkaline? Are they halogen, noble gases? So make sure you're able to do this. We'll work on this in class, do some coloring and get you caught up on that way. Until then, guys, take care. I'll see you in class.